In this episode of the Quantum on the Back of an Envelope series, we'll draw your attention to an interesting one-dimensional potential with a rather unusual property. Despite being attractive and infinitely deep, it has no ground state, and in fact, no quantized energy levels at all. Our discussion will be simple and intuitive. We'll rely only on dimensional analysis and won't need to solve the Schrödinger equation. Let's consider a quantum particle of mass m, moving along a line represented by the x-axis. On the left, its motion is restricted by a hard, impenetrable wall placed at the origin, where x equals 0. For x greater than 0, the particle is pulled toward the origin by an external force corresponding to a potential that is inversely proportional to the square of x. The parameter a is a positive constant that sets the strength of this potential. Now, what would we naively expect from this system? Based on familiar examples, like the particle in a box, the harmonic oscillator, or the hydrogen atom, we might expect a discrete set of allowed energy levels. In particular, we'd expect a ground state with energy E0 less than 0, and possibly a series of excited states above it, E1, E2, and so on. In some cases, like the hydrogen atom, the number of quantized levels can even be infinite. Surprisingly, these expectations are completely wrong. This system has no ground state, and therefore no quantized energy levels at all. We can understand why without solving the Schrödinger equation. All we need is some basic dimensional analysis. So what are the parameters in our system that carry physical dimensions? There are three: the Planck constant, the particle's mass, and the parameter a that sets the potential strength. If a ground state energy exists, it must have the units of energy and must depend on those dimensional parameters in some combination. Let's assume it's given by some general expression involving powers of those three quantities. Here, alpha, beta, and gamma are real numbers that are, for now, unknown. Any dimensionless constant doesn't matter for our argument, so we'll ignore it. To find out whether such a combination is even possible, we'll assign units to each quantity. We'll use m for the unit of mass, L for length, and t for time. The ground state energy E0 has units of energy, which are mass times velocity squared. That is m times L squared divided by t squared. The Planck constant has units of energy times time, which gives us m times L squared divided by t. The mass, of course, just has units of m. And the parameter a, as the coefficient in a 1 over x squared potential, must have units of energy times length squared. That gives us m times L to the fourth divided by t squared. Now that we know the units of all the dimensional parameters, we can work out the units of the proposed expression for the ground state energy. A bit of simple algebra gives us this result. We need to choose values of the exponents alpha, beta, and gamma so that the result matches the units of energy. By comparing these two expressions, we arrive at a system of equations that the exponents must satisfy. It can be readily seen that the last two equations are incompatible. This means that we can't form an expression for the ground state energy using the dimensional parameters available in this system. That tells us something profound. This quantum system cannot have a ground state, and if there's no ground state, there are no discrete energy levels at all. The 1 over x squared potential has many other fascinating properties. For example, for certain values of the parameter a, the system possesses a continuous spectrum of negative energy states that stretches downward without bound. This implies that such a system, if it existed in nature, would be wildly unstable. It would keep transitioning to ever lower energy levels, releasing an infinite amount of energy in the process, which could, in principle, destroy the entire universe. If you're interested in learning more about this intriguing quantum system, please take a look at this beautiful paper. We hope you enjoyed this episode of Quantum on the Back of an Envelope. To learn more about what we do, please visit us at our website.